it's only going to run from 2:30 to 3:30, and then there's going to be half an hour break, and then the prompt sessions will start from 4, not at 5. Okay, is that clear? Or then, okay. All right, so that's it. So today we're very happy to have. Oh yeah, one more thing. Yeah, there's a feedback form on the gear on our conference website. So you should all go and fill out the feedback form to tell us how we're doing. Okay. Okay. So again, we have Alex telling us about translation services, second part of his mini course today.
Okay, great. So I think the original title is something like Translation Surfaces and Their Orbit Closures, or at least that's the title of the survey I'm working off of. And so today we get to the orbit closure part. If you recall, last time we had several different definitions of a translation surface. And for today, the most elementary of them will suffice. Okay, so a translation surface is just a collection of polygons glued with sides identified in pairs up to some cut and paste relation. Okay, and the most important thing to remember from last time is that these come in a moduli space, okay, a parameter space. These parameter spaces are called strata. You fix the genus and you fix the cone angles and you get a stratum of translation surfaces of that type. And each stratum has a GL2R action. Okay, and the GL2R action, again, is a very easy action. The polygons live in the plane. GL2R acts on the plane. Okay, so the recent big theorem in this subject, which is due to Alex Eskin, Mariam Mirzakhani, and Amir Mohammadi, says the following. Every GL2R orbit closure is a manifold. Okay, this is really amazing. So some of you might be dynamicists, in which case I'm preaching to the choir. Some of you may be geometers, though. So I should sort of pause to remark. You know, a lot of math exists on this spectrum of complex analysis to real analysis that you learn in undergrad. In real analysis, you build a counterexample to everything. Okay? You think continuous functions are differentiable. No, basically none of them are, et cetera, et cetera. You name the statement, then you prove the counterexample. Whereas in complex analysis, you throw out some ridiculous sounding statement. You know, once differentiable function is infinitely differentiable, and it all turns out to be true. Okay, so sort of algebraic geometry is on this side. Dynamics is very much on the real analysis side. Okay? In dynamics, you don't typically prove theorems like this. You prove theorems like, you know, for any real number, there's an orbit closure with that Hausdorff dimension. Okay, they're sort of fractal objects. And so the big deal is that the orbit closures are really, you know, nice, understandable objects. If they were fractals, we'd, like, frankly, be sort of screwed in terms of really trying to figure out translation surfaces to the extent that we can now dream of doing with this theorem. Okay, a quick aside on this. Sometimes when people learn this theorem, they think, okay, great, what I need to do to start thinking about translation surfaces is to go read the proof of this theorem. Okay, frankly, that's probably a really big mistake. It's a 300-page proof, and it has almost nothing to do with translation surfaces. Okay? Really, if you're a student in homogeneous space dynamics, then maybe you should go read the proof because it's relevant for you. But if you're someone who'll be applying the theorem, then it's maybe the proof is not so relevant. It's extremely abstract. Which brings us to the fact that, you know, although it's a great theorem, it doesn't give us a list of orbit closures. Okay? It does say a little bit more than this, which is quite fantastic. And that little bit more is, so every orbit closure is a manifold defined by linear equations in the local coordinates from last time. So you remember, you present a translation surface using polygons. A collection of edges of those polygons give local coordinates. Okay, so not only is it a manifold, it's somehow a manifold that at least locally is very easy to describe. So just before I give an example, well, I'll say two things. So first of all, this object, a manifold defined by linear equations in the local coordinates, this is often called an affine invariant submanifold. Which is not a very good term. It's really more linear than affine, and affine makes algebraic geometers confused because to them affine is an affine variety. And also, for reasons I'll explain in a second, it's technically speaking not a submanifold, despite the lie that I told you here, the very minor white lie. A better term is just or GL2R invariant subvariety of the Hodge bundle. Okay. So first of all, subvariety. So each stratum is actually an algebraic variety, as you would expect since MG is an algebraic variety and the Hodge bundle is an algebraic variety. And Phillips showed that not only do you get these submanifolds, you actually get subvarieties. Okay, the other thing is, as I said, technically speaking, it's not a submanifold. It can have the mildest possible singularities in that two branches of it can cross themselves. Okay, so the easy way to resolve that is just saying it's an immersed manifold. Okay, so it is still a manifold. It's just sort of not, not actually a submanifold. It's an immersed manifold. It's a really minor issue that doesn't actually play a big role in this subject. Okay, so that's one comment. Another comment. So before I sort of hinted that this is sort of a ridiculous thing to try to prove because this is not the standard in dynamics. Okay, but this does come from somewhere, and they drew inspiration from a result of Ratner that says something similar for homogeneous spaces. Okay, and more recently, a result of Benoit and Quin, which uses a very different method than Ratner, but again, obtains some sort of similar rigidity result. Okay, and if you want to, if you really want to learn the proof of this, something about it, you should not try to read this paper. What you should do is you should read this paper. Okay, I can tell you later specifically which paper to read, because it's much, here you can read about a space that's the torus R2 mod Z2 and get an idea of some of the techniques. Whereas here there are many, many more techniques, and the space is very complicated. Okay, and frankly, already this won the Clay Prize for Benoit and Quin, so this already has enough ideas to start with, if you don't know them already. Okay, so on to an example. So let's look at one of these square-tiled surfaces. The example is square-tiled surfaces. Square-tiled surfaces. Just identify opposite sides here. So last time, I stated the result that the stabilizer of the square torus is SL2Z. Okay, so any matrix in SL2Z stabilizes the torus. You can very easily extend that to show that for any square-tiled surface, there's a finite index subgroup of SL2Z that stabilizes the torus. Okay? And you can use that to show this has a closed GL2R orbit. And if that isn't crystal clear right now, don't worry about it. We'll come back to that in about 10 minutes. But this has a closed GL2R orbit.
Do you have any hope of like constructing the finite index subgroup just from like staring at that picture?
Yep.
Okay.
Yeah, there's an algorithm to do that for you. That's very combinatorial. The reason people like square-tiled surfaces is everything about them is combinatorial and fairly computable. Yeah, so this orbit, what it looks like is GL2R mod the finite index subgroup. But as I said, I'll come back to that in a minute. So this is the easiest possible orbit closure, because in general, what an orbit closure is, right? By definition, you look at the orbit, which sort of goes around wildly, and then you look at its closure, like the set of all the points it accumulates on. And in this case, the orbit is just already closed. So it's somehow especially simple. Right, so anyways, there's a closed orbit, which in particular is an orbit closure. So it should be defined by real linear equations. OK, so I should have done.
Why is the orbit not? Why is it not GL2R mod the full stabilizer?
It is. So gamma is the stabilizer of the square-tiled surface, which is a finite index subgroup of SL2Z. So the stabilizer of a torus is SL2Z, but somehow the way in which the finitely many squares are put together can cause some finite obstruction to some specific matrix being in the stabilizer. Okay, so for you, I'll say that when you act by an element of SL2Z, you get another square-tiled surface with the same amount of squares. And there are only finitely many of them. So with some probability, you get the same one you started with. OK. So I'm going to draw this bigger, because I think I drew it a little bit too small. OK. So now I'm going to draw some local coordinates. V1, V2, V3, V4, and V5. OK, so those are some edges. At this point, we haven't really talked about this explicitly before, so you might understand, like, why don't I have all of the edges? In fact, I don't even have, like, OK, I guess I have one of every pair. So it's clear that it's enough edges. So these sort of V1 through V5, these are local coordinates for the stratum in which this lives. OK. So this covers the regular torus, just the usual square torus. And what happens is when you act by some matrix, you no longer cover the same torus, but you do cover a torus. So actually, you should act on this whole picture by that matrix. And for example, if you skew, this will skew, and this will skew also, but you'll still get a cover of a torus with sort of the same combinatorics. And at this point, I just want you to notice, so these two edges are the same line on that torus. Okay, and their preimages here are this, 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 and this. Okay? So if this is going to cover the torus, even if it's a slightly different shaped torus, then V4 should be equal to V5, okay, because they map to literally the same line on the torus. So one of the equations will be V4 equals V5. Okay, and similarly, those are the same lines. And all of these lines map to it So I should have v1 equals v2 equals v3. Okay, so these are the linear equations cutting out this orbit closure. Okay, and in general, it's similarly explicit. Questions so far? Okay, so I want to elaborate on actually what this says. Yeah?
Why do we want it to map onto the
It's just something that's true of the entire GL2R orbit. It's an observation. If I sort of hit the surface by some matrix, I can also hit the torus by this matrix, and this new surface will cover the new torus. Okay, and it will still be true that V4 and V5 map to the same line on that new torus, so this equation will still hold. Okay, so this.
Conversely, if those equations are satisfied, you should be able to see that you can chop the thing up into.
Yep. Yeah. So it's a good little thought experiment, right? You should try to wiggle this so that these equations hold and convince yourself that you still map to a torus. Okay. So now I want to elaborate a little bit on this statement here that I've underlined. Okay, and I'll be a little bit more precise. So actually, well, I'll write always. The linear equations have coefficients in R and 0 constant term. Okay, so in other words, you know, I could never have had like v1 plus 2 plus I v2 is equal to 4. That guy's doubly not allowed because this would have a complex coefficient and a constant term.
This is true for all GL2R.
For all GL2R orbits. Okay. And it will become clear momentarily why it's true. Okay. So the proposition I want to show that will make that clear is manifolds, submanifolds, are really subvarieties defined by such equations are always GL2R invariant. Okay, and actually I wrote it like this, but it's an if and only if. If you had these constant terms or something, you'll see in the proof that it wouldn't be GL2R invariant. Okay? So this you can think of as a converse. So this is an easy converse to the result I wrote above. Okay. So the proof will reveal a very helpful way to think about the dynamics of the GL2R action. Okay, so if v1 through vn are local coordinates given by edges of the polygons, right, vi equals x, vj equals xj plus I yj. Okay, so x is the real part and y is the imaginary part of the coordinates. And it's really helpful, it turns out, to write down the coordinates in this way. Okay, so I'm just writing it out as a 2 by n matrix. And the reason it's helpful to write it out this way becomes clear when we think about what happens when we multiply the surface by a 2 by 2 matrix A, B, C, D. Okay, well, you know this because really A, B, C, D is just acting as usual on the plane. Okay, and you know every vector in the plane you should write as a a column vector like this, and then it just acts via matrix multiplication. Okay, so this gives the coordinates of A, B, C, D times the starting translation surface with these coordinates. Okay, or another way people like to write this is they would just say that A, B, C, D of x omega equals x prime omega prime, and they would write something like, so I'll give you some competing notation now. Some people like one better than the other. So this is another shorthand for sort of just what I wrote here, the real parts and the imaginary parts. So this is A, B, C, D times the real part of omega and the imaginary part of omega. Okay, which means the new real part is A times the old real part plus B times the imaginary part. Okay, this is just the action of GL2R on the plane.
So there's no issue here that these are just local coordinates?
So there absolutely is an issue like that. Okay, very good. So only, well, let me say most meaningful when A, B, C, D is sort of close to the identity matrix, or at least not too large. So you stay in the same coordinate chart. Okay. So that's absolutely right. But to show you a GL2R invariant, it actually suffices to show you you're invariant under small matrices. And there's some general, topology thing you can do. Okay, so if the equations, by which I mean the equations defining the manifold, have real coefficients and zero constant term. So actually, this part just uses real coefficients. No, and zero constant term. Then so let me write this if V is a solution, so is the imaginary part of V and the real part of V. So here I'm just making a statement about linear equations in C. Okay, if you have some linear equations in C and you have a solution, and if the linear equations have real coefficients and zero constant term, then the real and imaginary parts are also solutions. Okay? And that means if you take a linear combination of the real and imaginary parts, then you'll also get another solution. Okay, but precisely what this and this is showing is that the coordinates that you get from something in the GL2R orbit are actually just a linear combination of the real and imaginary parts of the coordinates of the starting surface. Okay. So real omega, imaginary omega are solutions. So here, for example, what I want is I want sort of A times the real part of omega plus B times the imaginary part of omega plus I c times the real part of omega plus d times the imaginary part of omega. And this is just omega prime. This is what you get by applying this 2x2 matrix. Okay, and that's the whole proof. As I said, this converse is easy. Okay, and you see, if I didn't require the coefficients to be linear, or if I didn't require the constant terms to be 0, this wouldn't work. Okay, it wouldn't be true that you could take the real and imaginary parts and take some linear combination of them. Okay. So are there any questions about this? So one of the morals is that because the action is so easy to understand in the complex plane, it's just the usual action, the effect on coordinates, at least if you don't worry about sort of changing charts, is also extremely easy to understand. Okay, so while we're making friends with these orbit closures, let's remark that I said they're manifolds. They're really, of course, complex manifolds, right? Because the local coordinates look like Cn, and I'm just looking at some linear equations in Cn. So they're complex manifolds, so we can think about their complex dimension. And like one of the first questions you might ask is like, what could the complex dimension be? Okay, could it be 0? Okay, well, that's an easy one. Who can come up with an explanation for why the complex dimension can't be 0? It's like saying, could the orbit closure be a single point?
The stabilizer is never that big.
Yeah, you can always just move by some matrix, and it's not just a single point. Okay, we talked. This is what Jeff was referring to. Is last time we showed the stabilizer wasn't all of SL2R. So, for example, you could just scale it, and already that shows that it's not just a point. Okay, so dimension 0 is out. And the next question is maybe like, well, could it be dimension 1? Okay. And there's a good guess here. Who has a guess, or even a proof?
Complex dimension.
Yeah, could it be complex dimension 1?
Again, that's stable.
Yeah? So let me elaborate on that. So last time, again, we showed the stabilizer of a point as discrete, okay, which is, again, just these local coordinates. You're changing the local coordinates. And GL2R is dimension 4, real dimension 4. So that means your manifold should have real dimension at least 4, okay, which is complex dimension 2. So these orbit closures will always have complex dimension at least 2, and that's sort of the case where they're just given by the orbit. Okay, that's the lower bound. Okay, so let's talk about this some more. So closed orbits. If one of these guys, so I'll just write M, which is an orbit closure, or equivalently by EMM, one of these linear submanifolds. If M has complex dimension 2, it is a closed GL2R orbit. Okay. So, example, if gamma equals the stabilizer of x omega is a lattice in SL2R, then the GL2R orbit is closed. Okay, and how do you show that it's closed? Well, you actually just show that it's isomorphic to GL 2R mod gamma. Okay, just an easy application of thinking about the orbit map. Okay, so closed orbits are very special, and they've been studied since way before this theorem of Eskin-Mirzakhani-Mohammadi. And in a way, they provided a way around it. Okay, they showed that there were at least some surfaces with interesting orbit closure that we could understand. And it was sort of fairly elementary in many cases to compute the stabilizer of a surface. And so this sort of provided, really accessible examples. And I think really this was like one of the focuses of the field for a long time. Okay. So it's interesting. Here we see that it's, if you have a lattice, if the stabilizer is a lattice, the orbit is closed. And you might wonder, is the converse true? Okay, if the orbit is closed, does the stabilizer have to be a lattice? And it's sort of a good thing to ponder for a minute. Like, first maybe ponder, could the stabilizer be just empty? Okay, so you'd have that GL2R orbit that somehow doesn't accumulate. Okay, which sort of in a universal cover in a Teichmuller space could happen very easily. But in moduli space, you sort of expect it to wrap around. Okay, but still maybe it could wrap around but sort of go further and further out the cusp or something. So it's not even obvious that closed implies that the stabilizer is not empty. Okay, but Smiley proved the converse. Okay. And this is non-trivial. And in particular, it uses dynamics. This sort of is not some general principles thing, but you really need some dynamics to prove this. Okay. And for this reason, if x omega has closed orbit, it's called a lattice surface because its stabilizer is a lattice. Okay, people also call it a Veitch surface, a Veitch translation surface. I prefer lattice surface. Veitch is one of the fathers of the field, and he was so successful that everything is named after him, to the point where there was a paper that was circulated under the title, Veitch does not imply Veitch. So I think by the time you get to that point, they've gotten a lot of credit, and you can maybe just try to find meaningful notation for at least a few of the terms named after Veitch. Okay. And just to mention something that I haven't really mentioned before, this is sort of an aside. So recall, this space of translation surfaces lives in the Hodge bundle over mg. Okay, and there's this projection map that sends x omega to x. Because you have some space of translation surfaces that lives over mg, and you can just project. One of the many reasons that people were interested in closed orbits is because they project to some very interesting loci. So the projection of a closed orbit to mg, so this is via x omega maps to x, is an algebraic curve, which means it looks like just H mod gamma if you don't like algebraic curves. Algebraic curve means complex dimension 1. Isometrically immersed with respect to the Teichmuller metric on MG.
Sorry, I have a question from way before.
Yes?
So the fact that stabilizer is a lattice, that doesn't imply like trivially that the orbit is closed.
No, it's true. It doesn't imply trivially that the orbit is closed. However, it is general principles. So I can show you afterwards. There's like a point set topology type argument you need to make, which is actually a little bit tricky and goes unremarked on a lot, even though it is tricky.
Co-compact lattice is
If it was co-compact, it would be easy. But it's not actually. You have to prove that the orbit map is like a proper homeomorphism. Yeah. But it's although it's tricky, it is like in the grander scheme of things relatively easy, and also doesn't really have anything to do with moduli space. Yeah. Other questions? Yep.
Can this H-point gamma have more than one cusp?
Yes.
Yes.
Yeah, and it's very interesting how many cusps it has. It always has at least one, remember, because it's not co-compact. Yeah. Other questions? Okay, so I should tell you, this is called an isometrically immersed algebraic curve in MG is called a Teichmuller curve. Okay, so I'm not going to talk much about either algebraic geometry or the Teichmuller metric, but it's somehow all very closely combined when you talk about closed GL2R orbits. Okay. So So I want to talk a little bit about dynamics now, because really the dynamics of this action is one of the most studied things here. It's the powerful thing. And so I should give you at least a little bit of a feel for it. Okay? So far I've given you a tiny bit of a feel for you just by explaining that a surface can have a large stabilizer, okay, which sort of shows that the actions can sort of come back to itself. Let me start by talking about the dynamics of this one parameter subgroup, e to the t 0, 0, e to the minus t. Okay. So, well, maybe I'll start with part 0, which is just the dynamics of SL2R, broadly speaking. If H is a stratum, so a locus of all the translation surfaces with the same genus and cone angles, define H1 to be the unit area locus. So these are just the locus of unit area translation surfaces. Okay, so you could compute the area of a translation surface in terms of the coordinates. The unit area looks a little bit like a hyperboloid, okay, in local coordinates. Okay, this hyperboloid is like xy equals 1, and in the higher dimensions, you get something more like the sum of xi, yi equals 1, something like that. So this unit area locus is invariant under SL2R, and it turns out it has a very natural measure. So it has a measure called the Maser-Veitch measure, which you could also just call the Lebesgue measure. because it's what you would say the disintegration of Lebesgue measure in period coordinates to this unit area locus. Okay? So there's more than one way to say that. One way to very simply say it is if you want to compute the measure of a set on the unit area locus, you can cone it off like that and just take the Lebesgue measure of that. Okay. So why would you do this, and why would you restrict to the unit area locus? Well, at least this way, you have a chance for the measure of the whole space being finite. Okay, if you don't restrict to the unit area locus, then like you can scale the surfaces, and it's just obviously not finite, right? You know, Lebesgue measure on Cn is not finite. So this at least gives you a chance. It's not obvious that you actually get a finite measure, but Mazur and Veach showed that the sort of natural Lebesgue measure, which is now often called the Mazur-Veach measure, is finite. And to a dynamicist, having a finite invariant measure is a sign of rich dynamics. You have things like Poincare recurrence. Okay, so that was part 0 of our discussion of dynamics. So part 1 will be on more specifically the dynamics of this one parameter subgroup. Okay, if you're being sort of abstract, you can talk about the dynamics of any group action. But to be a little bit more classical and to connect with our notation as dynamics is something evolving over time, you should really have a process with one real variable. Okay, so this is called Teichmuller geodesic flow. And the reason it's called that is because its orbits, when you project them to mg, project to Teichmuller geodesics. So as I hinted at before, this GL2 action is very closely related to the Teichmuller geometry of mg in Teichmuller space. Okay. So I want to return to the coordinates we were using before, because they're really especially useful now. Okay, so I act on this by this matrix. And it's very obvious what happens. The real parts get bigger, and the imaginary parts get smaller. Okay. So for example, what you'd like to say is if I took two surfaces with the same real parts, and I looked at how they evolved. So I have one surface, and I have another surface that I get just by, say, nudging the imaginary coordinates. And I look at what happens when I apply geodesic flow. Well, let me just write this. So what I have is I have another, so I have this surface, and I have another surface, x1, x2. So the real parts are going to stay the same. And then I have y1, y2, up to yn. And I'm looking at this point. Okay, and I want to understand how these relate to each other. So intuitively, they should relate to each other just by taking the difference of the coordinates and then acting by the matrix. So this should be sort of, oh, sorry, these are supposed to be primes. I'm changing the imaginary parts. That's the whole point. And then I'll do minus y1, minus y2, minus yn. No, I did it totally backwards. Oh, no, and then it's zeros on the top now. There we go. Okay, so this, again, represents the difference of 2 points with same real part of their coordinates. Okay, so you have these 2 points whose real parts are the same, and you want to say that they get closer together as you apply GT. Okay, so what do you think? Is this a proof? Did I just prove to you that they get exponentially close as you apply GT? The coordinates are only local. And you're going very far away. Okay, so it's very hard to prove something asymptotic with local coordinates. Okay, so now enters the subtle part of Teichmuller dynamics. After you flow for a long time, you might sort of return to the same coordinate chart, or you might just be in some other coordinate chart, whatever. And now you should apply a change of coordinates. So before we saw change of coordinates just act by like some linear combination of the coordinates. Okay, so here the coordinates are the columns. And if I want to take a linear combination of the columns, then I should multiply on the right. Okay, so here I have a matrix which is the change of coordinates as I enter some new coordinate chart. There's no God-given coordinates, so you just have to like pick coordinate charts in some arbitrary way. So this depends on sort of t and on the surface you start with, and on your choice of coordinate systems that you've sort of used to cover the space. So this is where all the action lies, this integer matrix in GLN. So this is in GLN Z. And it satisfies what's called the Cocycle condition, which means if you want to know the change of coordinates after going for time t1 and then t2, well, you just compose them. Okay, so that's the condition for being a dynamical cocycle. And this is also called the Kontsevich-Zorich cocycle. And so I need to put it here too. So if you go to a seminar talk on Teichmuller dynamics, it'll, with decent probability, it'll be all about the Kontsevich-Zorich cocycle. Because, right, it's the hard part. It's somehow the linearization of this cut and paste operation, which is so mysterious. Okay, so I have a fight, sort of. The 2x2 matrix is doing something understandable that's desirable. Okay? The Kontsevich-Zorich cocycle matrix is doing something mysterious and, in general, ruining my ability to understand things. Okay? But thankfully, we get sort of lucky. And just to sort of summarize a long discussion, this guy wins and this guy loses. Okay. Which isn't to say he doesn't put up a fight and make things very interesting. Okay? So, for example, it is true that these 2 points will grow together exponentially, but not with rate e to the t, okay, because of the fight that this guy puts up. So I'm at the stopping point now, right? Is that? Yeah. Okay, so we'll take a break now, and then we'll resume in how many minutes?
15 minutes.
15 minutes, okay.